Now, we all know what a circle is. We'll just discuss on how we derive for area of circle. But before this, we just randomly discuss about what a circle is. We all know that a round shape with center equidistant from each of the points on this is called a circle. So when I have the center of the circle, the distance from the center to any point on this rim will always be equal, which is called the circumference of the circle. That is how a circle is defined. And the distance from the center to that particular rim is called radius. This is called radius, generally denoted with r. And this is called the center of circle. We all know every circle has a fixed center and a fixed radius. The radius which is equal in any direction you take. Now with this definition of a circle, we also know that circumference of a circle is given by the formula connected with radius as 2 pi r. This is the formula for circumference of circle given by 2 pi r, where r is the radius and pi is a value which is approximately 22 by 7 or 3.14, which we usually take. This is the value of pi. So using the circumference of circle, which is 2 pi r, we are going to now derive for area. Deriving for area of circle. So let's see how we can derive for area of circle. But before that, let's get into this concept where I divide the circle into totally 8 parts, where I just draw a line through the center vertically and horizontally and slantwise. Therefore, I get 8 different regions: 1, 2, 3, 4, 5, 6, 7, 8. So each of the region is called sector. This is called a sector because the part of the circle or the shape which is in terms of like a pizza. So the shape of a pizza is a sector. A circular pizza where one of the piece is taken out will be in terms of a pizza. So therefore, in case of this, which is cut in 8 different regions, vertically, horizontally and slantwise, all equal sectors are joined like this. So let's see how they are joined. So the non-shaded sectors are placed with their conical part with their edge facing upwards, and the shaded sectors are faced with their edge pointing downwards. Therefore, you get a shape which is in the form of upward, downward, upward, downward. So you have 4 sectors which are non-shaded: 1, 2, 3, 4, and there are another 4 which are shaded: 5, 6, 7, 8. So these are the 8 sectors which are broken from this circle and just joined here. Therefore, I assume that area of this entire region is nothing but area of the circle, because when you join each of the sectors back again, you get the complete circle. Hence, my attempt here is now to find area of this region, which indirectly would give me the area of the circle. So let's see how I can find the area of the region. So coming to this, if I assume this in a lateral form, this is in a slanting form, but when I assume this in the lateral form, I get this to be in the form of a rectangle. This forms a sort of an approximate rectangle if you just move it vertically straight. Therefore, this, when assumed to be a rectangle with length and width, then area of this rectangle would be length into width, which is nothing but area of circle which I am going to obtain. But what is the length and width of this rectangle which is indirectly obtained from this, exactly fitting in? Now the length is this which is assumed here, but when I take all 4 different sectors, I understand here that these 4 sectors form half the circumference. The 4 sectors, 1, 2, 3, 4, which forms the entire length of the rectangle, will in the circle form a half the circumference. 1, 2, 3, 4. So 1, 2, 3, 4, or 1, 2, 3, 4, and this 1, 2, 3, 4. So when I add all these 4 arcs of the sector, of the 4 different sectors of the shaded region or the non-shaded region, I get half the circumference. One full circumference, half of that would be 2 pi r by 2. So therefore, my length is half the circumference. So this is my length of the rectangle. And what is my width? My width is the radius, because this sector has the radius r, and each of the sector arc is different from the radius, where the length is r. So this would give me the radius of the rectangle. The width is the radius and the length is half the circumference. So for this rectangle, I would like to find the area of this entire rectangle, which is nothing but area of circle is area of above rectangle, which we have taken here, but area of rectangle is length into width, but my length is half the circumference. My length is half the circumference of circle, and width is the radius. The width is already calculated to be radius. So half the circumference being length times width, which is r, will give me the area of circle. So let's see how we get it. Half into, now the circumference of circle is already calculated to be 2 pi r. So this, when substituted as a formula, I get this as 2 pi r times r, as we carry from here. Now immediately when I cancel 2 and 2, I get pi r times of r, which is pi r square unit square. Therefore, area of circle is now derived with the formula A equal to pi r square unit square, where r is the radius of the circle and pi is approximately 22 by 7 or 3.14. This is how we obtain the circle from sectors indirectly forming a rectangle. So a circle is associated with a rectangle, and hence area obtained here. Now we have derived formula for area of circle, which is pi r squared, and circumference of circle, which is 2 pi r. Similarly, we'll also find the area of circular path, which is indirectly derived from a circle. So what is a circular path or a ring? So let's see the shape of a ring or a circular path. So when I have two concentric circles, circles with the same center, say this is my circle 1 and this is my circle 2. Now they have the same center, therefore they are called concentric circles. Now in this kind of circles, this is called the area of the ring or area of the circular path, where this is not included in between or outside, something like a donut. This is something like a 3-dimensional donut. So in this case, I had to find area of this circular path. So to find area of this circular path, which is a ring or a circular path, I just use the areas of the circle. So let me imagine my bigger circle has the radius capital R and my smaller circle has radius small r. So outer circle, which is this, has radius r, and inner circle, which is a smaller one, has the radius small r, and the centers are same. So using these two dimensions of the bigger radius and the smaller radius, let's find area of the circular path. Now how do you find area of outer circle? It is nothing but area of circle. So the area of outer circle is area of circle with radius capital R. As we already know that area of circle is pi r square, so my area in this case of outer circle is pi r square with the radius being capital R. Similarly, my area of inner circle would be the pi r square with the radius of inner circle being small r. Therefore, area of inner circle is pi r square with the radius being small r. In this case, capital R for outer circle. Now, as I know the area of the outer circle and area of inner circle, now area of the shaded region is obtained by subtracting the area of the inner circle from the outer circle. If I remove the inner circle from outer circle then I get only the shaded region or the rim or the ring of the region which is shaded out here. Therefore, when I want to find area of circular path or a ring is area of outer circle minus area of inner circle. So this is how I obtain, as can be clearly seen in the geometrical concept of the diagram. Outer circle minus inner circle gives me area of the shaded region or the ring region. So therefore, as we already calculated for outer circle the area to be pi r square with capital R, substituting in place of the first area pi r square minus area of inner circle is calculated to be pi r square with smaller radius, substituting in case of the smaller circle, I get this. Then on further simplification of this, I get pi times of r square minus r square. Therefore, area of the required circular path is pi times r square minus r square. But when I still further simplify, I know that by the identities which we already discussed in the previous sessions, a square minus b square is a plus b times a minus b. Therefore, r square minus r square can be written as r plus r times r minus r unit square. So this is how the area of the circular path or the area of ring is obtained from the given dimensions. Now, semicircle is half the circle. We all know that a semicircle is half of the circle. So let's find area and circumference or perimeter of a semicircle. So when I just take the semicircle, the definition says that it is half of the circle. Therefore, when I take the center, the half part of the original circle is nothing but the semicircle. The original circle where half of it is cut, this is the semicircle with radius r. Then this would be the diameter, twice of the radius, which would be diameter from here to here. Now when I know the radius of the semicircle, I can find area or perimeter. First, let us start with perimeter of semicircle. As we know that circumference of a circle is 2 pi r, half the circumference is this, the curved path from A to B, which would give me half of 2 pi r, but I had to include even the line from A to B, which is the diameter, in finding the perimeter. So my perimeter would be from here to here and then here to here. Therefore, this is half the circumference of circle plus the distance AB, which as I can clearly see in the diagram. Now this is nothing but half times of circumference of circle, as we all know, is 2 pi r plus the distance AB is 2r, because r plus r makes the diameter AB. So I can find the perimeter of semicircle by taking half the circumference of circle plus AB, where the circumference of circle is 2 pi r, which when substituted in this formula gives me half times of 2 pi r, plus AB, which is the diameter, is twice the radius, hence 2r. Now when I cancel these two, I get pi r plus 2r. Therefore, my perimeter is r times of pi plus 2 units. This is how the perimeter of a semicircle is obtained, r times of pi plus 2. Now similarly, area of circle, semicircle, is nothing but half the area of circle. It is exactly half the circle, therefore its area is also exactly half. But we know that area of circle is pi r square, half gives me pi r square by 2, which is the area of semicircle. Similarly, we can construct the perimeter and area of a quarter circle, which can be like this. This is 1/4, so wherever I had half, that would reduce to 1/4, and the formula which is obtained for perimeter or area depends on 1/4 of what is simplified with 1/4. Therefore, we can construct for any quarter circle or 3 quarter circles or semicircle or even the complete circle. So this is how we find the perimeter and area of a circle or a semicircle or a quarter circle or a three-quarter circle. So length of arc is something which we're going to see now in this session. Now before this, what is the length of the arc? It is part of the circumference which we identify in part of the circle. So let's see what is an arc through the geometrical concept. So if I take a circle with center and a suitable radius, then if r is the radius of the circle, then from the center, if I join, this is the sector, and when I just extract the sector, this length is called length of the arc, and the length of the arc is very much associated with its angle theta. So let's see how the length of the arc and angle are associated in terms of the radius of the circle r. So assuming this to be the length of the arc, so we have a formula which we are going to derive through the conjectures. So let's initially start with the whole circle. If my whole circle has, say for example, if I take the entire circle, my whole circle has the angle as 360 degrees. Therefore, this on completion of full 360 degrees will give me the angle theta as 360, which is the angle, and this in terms one full 360 degrees gives me circumference. Therefore, my length of arc in this case would be circumference of circle, which is nothing but 2 pi r. So my circumference is 2 pi r, but I write this as 360 by 360 into 2 pi r because I just want to bring in a conjecture through the angle associated with the radius. So let me write this 2 pi r as 360 by 360 into 2 pi r. Similarly, I take a semicircle of radius r. Therefore, in this case, my angle is 180 degrees. So in case of a semicircle, my angle is 180 degrees. So I get in this case my length of arc. This is the length of the arc, the whole of the length of arc here. In this case, this being the length of arc in this case is half the semicircle, half the circumference of circle, as we already discussed. Half the circumference of circle, which on further simplification gives me half times 2 pi r, which is nothing but pi r. As I written pi r in 2 pi r in terms of the angle as 360 by 360 to 2 pi r, I write pi r as 180 by 360 into 2 pi r, so that when I simplify this, I get back again pi r. So I want to express all the given angles in terms of by 360 into 2 pi r. I want to make this a common term in each of its derivation. So here I get 360 by 360 into 2 pi r. I get here 180 by 360 into 2 pi r. Then I also take next as x. So let me take this with 90 degrees, a quarter circle, so that this is 90 degrees and this is the length of the arc. Therefore, in this case, my theta is 90 degrees, as I can see here, and my length of arc in this case would be length of arc is 1/4 of circumference, because this is 1/4 of the whole circle which is taken into consideration. So that's the reason I get 1/4 of circumference of circle, which is 2 pi r, so that I get this as 1/2 times pi r, and this in conjecture can be written as 90 by 360 into 2 pi r. This on simplification gives me 1/2 pi r. So every of the constant written in the form 2 pi r by 360 times of angle, I obtain a conjecture in a form that whenever I take 2 pi r by 360 multiplied with this angle is nothing but length of arc. So whatever is the angle I consider here, that is to be multiplied to 1 by 360 times 2 pi r. So in this case, because this angle is 180, 180 is the angle I multiply to 2 pi r by 360. Here the angle is 90, so 180 by 2 pi r by 360 is multiplied with that angle 90. Similarly, if I have theta is 45 degrees, then that implies the length of the arc is multiplied with 2 pi r by 360 of this angle coming here as 45. So this is how I obtain the conjecture for length of arc. Therefore, in general, I observe that if I have a sector with length of arc as L and radius as R and my angle is theta, then in this case my length of arc is given by the formula. In general, it is given by the formula theta by 360 into 2 pi r, with this being same. So this is how I obtain the length of arc, which is theta by 360 into 2 pi r, as can be seen through the conjecture of each of the cases of 360, 180, 90, 45, etc. So in general, for any theta and the radius r fixed for the circle, the length of the arc denoted by L is given by the formula theta by 360 into 2 pi r. So length of the arc associated with angle in this form. So let's see an alternative method where the area of, or where the length of the arc is calculated connected with an angle. We have seen that the length of the arc was obtained as theta by 360 into 2 pi r. So there's another alternative method through which the length of arc can also be calculated for the given angle theta and the length arc and the radius r for the given circle. So let me divide this into a sector and a circle. Now let me take the circle independently, where the radius is r and the angle is 360 degrees and the whole of the circumference is 2 pi r. So the whole of the circumference is 2 pi r and the angle, whole of the angle is 360 degrees and the radius is r. Now let me take part of this circle, which is a sector, in this form. So I have a sector with its length of arc as L and the radius is r and the angle is theta degrees. Now the two of the circumferences and angles are in same proportion. Therefore, because sector is part of the circle, they are in same proportion. Therefore, their angles and their arc lengths are in same proportion. If I take the arc length of the entire circle, which is nothing but circumference, the arc length of circle divided by arc length of sector, which is obtained here, is nothing but angle subtended at center by the angle subtended at center of sector. This is for circle and this is of sector. So this is how they are proportionally equal, connected to lengths of arcs and the angles. So using this formula, I clearly have arc length of circle is nothing but circumference and hence 2 pi r. And the arc length of sector is already taken as L, so I substitute L in terms of arc length of sector. Now as this is equal to angle subtended at center of circle, I can see that angle subtended by the whole arc at the center is 360 degrees, because one full angle in a circle is 360. Therefore, the subtended angle at center is 360 degrees. And the subtended angle of sector at the center is clearly theta degrees. So this would be correspondingly theta degrees. And when on cross multiplication, I get this to be, on further simplification, 360 times of L is theta times 2 pi r. this on, taking L to the left, the remaining term to the right, I get theta by 360 into 2 pi r as the length of the arc, which is nothing but the same formula which is obtained in the previous session for length of arc. So this is how we find the length of arc connected with angle. There are various methods through which the formula is derived, this being one of the methods. Now, as we found the length of arc, we'll also find the area of the sector with its subtended angle as theta, and the length of arc is L and the radius is r. So in this case, we connect the area of the circle with that of area of sector. As in the previous case, the length of arc was connected with length of the whole circle arc, which was circumference, connected with the angle. So in this case, areas and angles are connected to be in same proportion. Therefore, if I just divide this into two of these whole circle and then into the sector, then I observe that the radius being r and r, this being theta, the whole angle here would be 360 degrees. So the angles and the areas of the circles would be in same proportion, with this being the length of the arc of the sector. So areas and angles of the circle and sector, the circle and the sector, areas and angles are in same. Now, since areas and angles of the circle and the sector are in same proportion, that is, the similar angles and the similar areas of the circle and the sector respectively are in same proportion. Therefore, mathematically, I have area of sector divided by area of circle are in same proportion. Thus, this being equal to angle subtended at center by the sector. So, angle subtended at the center by the sector by angle subtended by the circle at the center are in same proportion. So let's see what each of them are. Now, because I had to find area of sector, I take the area of the sector as A and area of circle is already known with radius r to be pi r square. So by substituting the formula of pi r square as the area of circle, I get angle subtended at the center by sector is clearly theta degrees. Therefore, this would be theta, and angle subtended at the center by circle is the whole angle, which is 360, which is subtended at the center by the whole circle. Therefore, this comes to be 360 degrees. So area of sector is obtained by taking this in same proportion of areas and angles. Now with this, when I take this term to the right, I get area equal to theta by 360 into pi r square, which is nothing but area of the sector of subtended angle theta and radius r. So this is how we obtain the area of sector. Now, how do you connect this to length of arc? So let's derive this formula using the length of arc. So when I want this in terms of L, the length of arc, which is here as L, let's see how we can obtain the area of sector in terms of L. So I just write this as theta by 360 into 2 pi r into r by 2. I just multiplied and divided by 2 with one of the r taken along with pi inside and one of the r is taken out. So r square written as r times of r, one is in and one is taken out, and this is how I obtain theta by 360 into 2 pi r times r by 2. With 2 cancel, again I get back the same original. But the reason why I wanted to multiply and divide with 2 and split the r is I have a ready-made formula for this, which we have derived in the previous case, where this was length of arc, which was derived with the formula theta by 360 into 2 pi r. Hence, this is length of arc, which is nothing but L. So So in place of this I substitute L so that I get LR by 2. Therefore, my area of sector in terms of length of arc is obtained as A equal to LR by 2. So area of sector in terms of angle is theta by 360 into pi r square, and area of sector in terms of length of arc is L times R over 2. So LR by 2 unit square. Units are very important when we write the areas and perimeters.